tens of mega ohms are higher. Okay, so usually we make use of the ohms law to find out the resistance B is equal to IR. So for B is equal to IR, either we have a constant regulated supply and we can measure the value of I, we can find out the value of R. Or we have a constant source, so we know the value of I, and if we can find out the value of B, we can find out the value of R. Okay, so this involves the use of either a current source, constant current source, or a constant voltage source, constant current source with a voltmeter and constant voltage source with an ammeter to find out the value of R. Okay, but theoretically it's okay. This technique works fairly well as long as the value of a resistance to be measured don't bring into question the ideal nature of the equipment, that how ideal an experiment is. Now the question is, what is meant by ideal current source? An ideal current source should drive a constant current through the circuit no matter what the load is. We discussed in the first lecture. But practically, the constant current that can be delivered is a function of load beyond a certain limit. We saw a graph that it becomes a straight line and then it comes down. Okay, so that is practical constant current source. Similarly, ideal voltmeter should have infinite internal resistance so that the current passing through must be equal to 0. The discussion regarding 2 probe and 4 probe. Okay, but practically it has a very high internal resistance, so the current passing through it is comparatively negligible. Measurement of high resistance of the order of mega ohms is basically a challenge for the ideal nature of these two. Okay, because if you are going to measure, because one could use a constant voltage source and emitter capable of measuring very low current, because we can take a limited power supply. The value of I is B over R. Okay, so I is equal to B over R. We can set the value of B to be equal to 10 volt, 20 volt, 30 volt, 100 volt. But since the resistance is mega ohm, so 10 volt or 100 volt divided by mega ohm will be a very small current. So that is again a challenge to measure the value of such a small current. So in general, it is not possible to apply Ohm's law to find out the resistance, any resistance. Is this clear? Because you are applying 10 volts or 100 volts, 100 divided by 1 mega ohm. So 100 divided by 1 mega ohm means 10 to the power minus 4. Okay, if you further increase the current, if you further increase the resistance, the current will further come down, and that becomes a problem for measuring the low current. In fact, in this course, you are going to see the measurement of resistance over these 4 ranges. One is, I am going to discuss about this one. If your resistance is of the order of 100 mega ohm or more, we are going to use discharging method. If we are going to have a resistance of this order, some mega ohm, the previous discussion on determination of band gap of silicon chip, we use a constant current source. Silicon chip, we make use of 9 volt. If you want to measure the current, resistance in this range, we can make use of a constant current source, we can measure the voltage. But if you want to go less than 10 ohm or 1 ohm, then we make use of a device called a lock-in amplifier that will be discussed by Professor Srinivasan in his lecture on lock-in amplifier. That is a very interesting experiment by which we can do a lot apart from measuring the low resistance, and you will be doing one experiment on the measurement of low resistance. Okay, here physics is very simple. If you charge a capacitor, okay, the charging will take place according to the equation Q is equal to Q0, 1 minus e to the power minus t over RC. RC is the time constant. So then we allow it to discharge through a resistance. Then the voltage Pt, voltage across the capacitor, Pt decreases as a function of time. So Pt is equal to V0 e to the power minus t over tau. Okay, so in this experiment, what we will be doing is, we will find out the value of Pt. We are going to charge the capacitor first, and then we will allow it to discharge. Okay, and when it discharges, we are going to measure the voltage across the capacitor by a function of time. And then this is the formula, T is equal to RC. Then we will plot a graph between ln of B. You take a natural log of both sides. ln of B is equal to ln of B0 minus T over tau. So you plot a graph between ln of B and T. The slope of the graph will give you RC or 1 over RC. And from 1 over RC, if C is known, we can find out the value of R. So that is the simple physics behind the experiment. Okay, that is what is written here. But what we do here is, okay, we are making use of pendulum capacitor in this experiment, which has an internal resistance of the order of few hundred mega ohm. Okay, that means you charge a pendulum capacitor and you leave it to discharge. So it will discharge because of its own high resistance. So what we will do, we will first allow the capacitor to discharge because of its own resistance, and then we are going to take an external resistance. Suppose R is the external resistance that we want to measure. Then we are going to connect this R in parallel with the capacitor. So therefore the total resistance becomes 1 over R double prime to be equal to 1 over R plus 1 over R dash. Okay, so first the external resistance is not inserted. So R double dash is R dash. So 1 over tau dash is 1 over R into C dash. Now R is inserted, so the total resistance becomes 1 over R dash to be equal to 1 over R. We are going to find out the value of 1 over tau and 1 over tau dash, and from these two we can find out the value of R. So in place of doing the first part of the experiment, we are going to repeat the experiment twice. We first repeat the experiment with the capacitor at its own. We allow the capacitor to discharge, okay, first because of its own resistance. So it will discharge, we find out the slope. Then now we connect the resistance to be measured in parallel to it. So resistance now changes. Okay, so we will again charge the capacitor and allow it to discharge. And from the slope of the two, we will be able to find out the external resistance that we can measure. Okay, so slope first and the slope second, the difference of the two is 1 over RC, and the value of R can be obtained by this one. What we need is, we need a high resistance by leakage circuit. So that is basically this box. I will explain you. And then we need a digital multimeter which is capable of measuring 2 volt DC up to 3 decimal place. This is basically the circuit here. Okay, it's better if I explain it from here. You can see there is a place for digital multimeter here. So these are the terminals. We have a on-off switch. Then we have digital multimeter. These are the leads. We have this knob. When you put it up, we can charge the capacitor. Okay, so there are 3 capacitors: 10 microfarad, 47 microfarad, and 100 microfarad. So we can select the knob. Okay, we have a knob here, so we can select the knob to the required value of the capacitance. So you are going to perform the experiment for all 3 capacitors. So first of all, you select one capacitor, let us say 10 microfarad. Here we have basically this switch. This switch helps us to find out the value of internal resistance which is inside the box. At the same time, it also gives us the liberty of connecting our own resistance also that we can measure. So here these 2 terminals are, what is written here is external. External means we have to put this knob down. Okay, and now we can put the external resistance here to be measured. Otherwise, whatever is there inside, we are going to put it in the internal mode and we will measure the internal resistance which is inside the box. Okay, so we have a choice of resistance. Either you can put the resistance here from your pocket, or you can measure the resistance inside the box. You are measuring the resistance thrice by selecting the first capacitor, second capacitor, third capacitor. So there should be consistency in the result. Okay, so that you can see from here also. Okay, we have basically these 3 choices for the capacitance. We have a digital multimeter. We have a switch here, internal. Internal means the resistance inside is to be measured. External means we have to put it down, and then we have to connect an external resistance here. This knob here is, if you put it up, you are charging the capacitor. If you put it down, you are discharging the capacitor. This O and S, if you are going to put it in O mode, then the capacitor will discharge because of its own resistance. But if you are putting it down to S, that means this resistance, internal resistance here, is coming in parallel to the capacitance. Okay, so you are performing what you will do in this experiment. You are going to first select a capacitor, let us say it's 100 microfarad. You just put it to charge, you switch it on, okay, and put this to charge, wait for 2-3 minutes, let it charge, and now you have to switch it to discharge. But before you start discharging, you must have a ready stopwatch in your hand, because you have to find out now the voltage here, because this is a digital multimeter. Digital multimeter will measure the voltage across the capacitor as a function of time. Time will be measured by stopwatch. Okay. Also, when you are going to measure the voltage across the internal resistance by using this DMM, there is one more switch here. This is PS. Okay. It is basically a push switch. When you are going to measure the voltage across the capacitor, you have to press this switch, then only you are going to measure the voltage in DMM. Now what is there basically behind this? This PS or this press button, okay, in fact there is a buffer circuit below this. Buffer circuit is an amplifier of unit gain. I hope you all know about buffer circuit. Buffer circuit is a circuit of unit gain, but high input impedance and low output impedance. Gain is 1. Whatever you apply here, you are going to get the same thing here. The problem here is we are going to measure a very high resistance. Even if it is discharging, the voltage across the resistance, okay, because of larger resistance, if we are going to put a digital multimeter here, the internal resistance of digital multimeter is of the same order of the resistance here. So we will end up with wrong result. We discussed, in fact, if you want to measure the resistance of a voltmeter must be infinity. But here we are measuring a very high resistance. So there is a problem of impedance mismatch, because this resistance is comparable with the resistance that we are going to measure. So what we have to do, we are going to feed the voltage drop across the capacitor, okay, across the resistor, across the capacitor here to our buffer. So buffer basically throws away the signal from higher impedance to lower impedance side, and we can measure the voltage by using this digital multimeter onto the lower side. So the problem of measurement is over. Okay, किसी भी voltage को if you want to measure the voltmeter resistance must be much larger than the resistance across which you are measuring the voltage. Here we are measuring the voltage of the capacitor, but capacitor is tantalum capacitor. Its internal resistance is very large. So if we want to measure the voltage directly, the resistance of a voltmeter must be very large as compared to the internal resistance of the capacitor. So that is why we are going to put a buffer circuit. So buffer circuit comes to action. Okay, buffer amplifier comes to action here when we press the switch here. You will press the switch and then you are going to take the reading. Okay, so voltage across the capacitor decrease exponentially with time constant Rc, where R is the high resistance. This output voltage across the capacitor is measured with DMM connected to the terminals. I have already told you. Between the ends of the capacitor and DMM, there is a voltage follower circuit. Voltage follower and buffer are the same thing. This acts as a buffer between the ends of the capacitor and DMM. This is necessary because input impedance of DMM has the same order of magnitude or even less than the high resistance that is being measured and will short the high resistance. Okay, the input impedance of operational amplifier is higher than the resistance to be measured. The button switch PS, that is push switch, when pressed connects the buffer plus DMM. The voltage across capacitor applied to the input of the voltage follower and the output of the voltage follower is measured by DMM in DC 2 volts range only at the time of measurement for short time and isolates them other time. This ensures that other resistance effects don't come in parallel with the unknown resistance and gives rise to the error in measurement. So this is the precaution that we have to take. We have to measure the voltage every time after pushing the PS switch. Okay, toggle switch internal to measure the internal resistance connected. I have already explained you. Select band switch position for required value of capacitance. So you have three choices for the capacitance. DMM in DC 2 volts has to be connected to the banana terminals. Switch on the mains. Toggle switch 2 is put to charging condition and charge the capacitor for 5 minutes. Check if the charging is over by pressing PS and measuring the voltage of the capacitor, say 2 volts. Okay, toggle switch now 1. Now use the toggle switch 2 to discharge in order to discharge the capacitor and set the timer. So then you record the voltage after every 5 minutes by pressing PS, that means the post switch. Then secondly what you do, capacitor is charged again by putting toggle switch to CH, but now the position is S. Okay, we again have to discharge, but now the readings has to be taken in 2 minutes interval because of change in the value of time constant. Because time constant will now change. Okay, capsule will discharge. Okay, and you again have to record the voltage as a function of time. So you have two set of data. You plot the log of B versus time. Find out the straight line. Find out the slope alpha and for S. Okay, the difference of the two will give you the value of R. These are the readings. Okay, switching O position and S position. O position means we are not adding any resistance. This is we are putting a resistance in parallel to the capacitor. So we are going to generate two set of readings. We plot them. This is how the graph looks like. This is one straight line and this is another straight line. You find out the slope of this and the slope of this. The difference of the slope will give you the value of the capacitance. These are for two other, and these are the values of the capacitance: 100, 47 and 10. These are the value of R dash. These are the R that we are going to measure, and from this we can decide which capacitor will suit for what range resistance measure. Okay, because you can check the error. Here error is 1.8%, here the error is 7%, but for this error is 0.9%. So error will be decided which capacitance you are going to measure for which value of the capacitor. Because capacitor also has an internal resistance, so you can compare the two. The value of R dash in the three cases are also different. Here it is 1401 into 10 to the power 6. That means this much of mega ohm, 102 mega ohm, and this is 3000 mega ohm. So you have to do this experiment between during the time when you attain the steady state. So that is all about these two experiments. Any question on this?
When we are pushing a PS button, it is inserting impedance in circuit.
It is inserting. In fact, what happens is if you insert it, a voltage follower circuit is there.
That is not affecting the current inside.
No, voltage. It is basically whatever you feed. It is basically an amplifier. Voltage follower is an amplifier of unit gain. Buffer circuit is also an amplifier of unit gain, but high input impedance and low output impedance. So you are simply throwing your signal from higher impedance to the lower impedance side. Because your problem is you can't throw away your voltmeter, you can't throw away your digital multimeter that has a fixed resistance. Okay, so the signal that we want to measure, we are shifting it from high resistance to low resistance. So low resistance, there will not be any problem on measuring the voltage, and we can measure it.
If you connect permanently, then come again. Whatever is the impedance will come. So we don't want that. That is the reason for pushing.
Okay, rest of the things we will discuss when you will do the experiment. I think there is no problem to be more than the problem will be right.